Good day to the panels. I'm Thulasy Chandran, final year Electric and Electronics Engineering undergraduate student. My supervisor is Dr. Omar bin Abdulaziz, who supervise and oversee the conduct of my project. Today I will be demonstrating my final year project, which is on the investigation of shielding effectiveness using transmission line analysis at sub 1 GHz. So the main goal of this project is to perform the study of absorption loss and shielding effectiveness via transmission line analysis for different materials. Other than that, to study shielding effectiveness for investigated materials at sub 1 GHz frequency range and to make absorption loss comparison via the transmission line analysis and simulation using CST Studio Suite. Finally, to make shielding effectiveness comparison between the single layer and multi-layer shield. Let me start with the first step of the project where we identify the suitable materials for the shield using transmission line analysis. The material was chosen based on the good conductivity. We know that a good conductor shows a phase angle of intrinsic impedance of 45 degrees. In order to determine intrinsic impedance was calculated based on the Maxwell equation. The table shows the material that were chosen initially, which are copper, stainless steel, carbon, aluminium, ferrite, gold, silver, and lead, along with their conductivity, permeability, and permittivity. Now let's have a look at the values and graphs obtained for each material for frequency range 50 MHz until 1 GHz. As you can see, the phase angle for each material of 45 degree was obtained. Based on the results of intrinsic impedance, it can be discussed that materials that have been investigated as shield are good conductor as their phase angle of intrinsic impedance is 45 degree. Next, using the intrinsic impedance of each material, the absorption loss, reflection loss, and multiple reflection loss for single and multi-layer was determined via transmission line approach. Figure 1 shows uniform plane wave impinging on a shield of finite thickness d and of infinite transverse dimension, while Figure 2 shows uniform plane wave impinging on a planar multi-layer shield and equivalent transmission line model. The first term, reflection loss R in equation, depends only on the free space impedance Z0 and the impedance of the shield medium Zs, and it accounts for the first field reflection at the two shield interfaces that is due to the mismatch between the two impedances at both the interfaces. The second term, A, absorption loss, is a function of the shield characteristics only, and it accounts for the attenuation that a plane wave undergoes in a traveling through an electrical depth equal to wave number Kxs equals to K0 in the shield material. The last term, M, multiple reflection loss, is associated with the wave that undergoes multiple reflection and consequent attenuation before passing through the shield. Now let's look at the graph obtained for both losses, reflection loss and absorption loss for frequency range 50 MHz until 1 GHz for single layer. For single layer shield, as you can see, as the frequency increases, the reflection loss decreases while the absorption loss increases. The reflection and absorption losses are both double those of the value of a single layer with same material and thickness. However, the multiple reflection loss differs from the double the value of a single layer. This is the result obtained for absorption loss and reflection loss of the multi-layer shield for frequency range 50 MHz until 1 GHz. With the same material and of the same thickness of multi-layer shield, it can be seen that the reflection loss and the absorption loss terms are exactly twice those of a single layer shield. Using the CST Studio Suite simulation software, the absorption loss measurement process was performed to make comparison between transmission line analysis and the simulation obtained. Copper as an agent for shielding material was used. The simulation process started by designing the shielding material with dimension of 150 x 150 mm and a thickness of 0.25 mm. On both sides of the material, the receiver and a transmitter antenna are located facing each other. The distance between the transmitter and receiver is 197.82 mm. The probe received the plane wave acts as a source of electromagnetic field, and the field force penetrated through the shielding material. As for the simulation of shielding effectiveness, we analyzed the S11 and S12 parameters in order to calculate the absorption loss. The absorption loss obtained for copper at 100 MHz for single layer is 153 dB based on the formula. While using the transmission line analysis, the absorption loss at 100 MHz was 328 dB. There might be some aspects that may not be entirely correct for simulation setting, resulting in difference on the absorption loss obtained by the transmission line analysis and simulation by the CST Studio Suite. Summing up the absorption loss and reflection loss for both single layer and multi-layer shield, it can be seen that the shielding effectiveness increases as the frequency increases. Based on the result obtained, it can be concluded that shielding effectiveness can be increased if the shield is made up of materials that are not only having high conductivity but also high permeability property as well. It is obvious that shielding effectiveness levels in excess of 100 dB are generally not achievable and also not measurable without extraordinary efforts. The preceding figures represent the trends of reflection loss and absorption loss, and they should be interpreted in the sense that above certain frequencies, such quantities exceed any reasonable threshold of shielding level. Multiple shielding layers provide a greater shielding effectiveness than a single shield. Because of successive reflection in the interspace between the two shields, the total decibel value of shielding effectiveness is less than the sum for the separate shields. Overall, stainless steel exhibits strong absorption loss and reduced reflection loss, which make it as a suitable material for shielding for both single layer and multi-layer shield. That's all from me. Thank you.